So we're going to start off, we're going to talk about what is depressurization, what it means to depressurize something, as well as then we're going to look at adiabatic specifically. Usually when we talk about depressurization, there's two types we talk about, adiabatic and fire case. These are not the only two types. We will mention that a little bit, but we will be focusing on these two types predominantly. Okay? We're going to start off talk about what is depressurization. We're going to talk about adiabatic depressurization, then fire case depressurization. So depressurization, that's the system, just like the name sounds, of taking a system at pressure and lowering the pressure of the system. You usually do this through the removal of mass from the system. If we want to be completely technical, it is not the only way to depressurize a system. You could lower the pressure through other methods. It is by far and away the most common method. So you generally do it, as I said, through the removal of mass, usually through a valve of some kind you have on your vessel. Generally, when we talk about vessel depressurization, we're talking about vapor, but it does not have to be. There are a number of other methods of relieving the pressure. One method that you do see with some frequency is something called a thermal expansion valve. That's usually when you have a liquid line and you are expecting in that liquid line some sort of thermal expansion due to temperature, and so you have a very small relief valve to allow that liquid to come out. Usually that relief valve is very small. Usually when you're doing pressure relief, you are doing it through the vapor. The amount of vapor you can relieve or fluid you can relieve is going to be limited by your valve. If you have a very small valve, you're not going to be able to get a lot of fluid through it. By your relief line, if you've got a very large valve but it's relieving into a very small pipe, you're not going to be able to relieve more than that pipe will allow. Similar with your back, it's going to be limited by your back pressure. If your back pressure is very high, you're not going to be able to depressurize very fast, etc. You're limited by the constraints of your system. Okay? Usually when we're looking at these, the primary things we will look at will be our valve, the line we're relieving to, and the back pressure. When I say valve, I'm using this as sort of a catch-all term for it could be a valve, it could be a ruptured disc, it could be something along those lines. Some immediate means of relieving our pressure. So the first thing we're going to look at is adiabatic depressurization, and we are going to do it the hard way. What I mean by the hard way is we are going to manually take a vessel and we are going to run it through a number of increments as we are going to manually do the calculation and find out what's happening to our pressure step at a time. We are going to do it the hard way, not because it's easy, but because it will accent what we're doing and why we're doing it. Okay, it will help us understand the theory of what we're doing. So we are going to be doing it the hard way. We are going to be doing it manually so we can understand the theory behind it. What goes into depressurization? Once we've done it the hard way and hopefully learned how to do it, we are then going to show you how to do it the easy way in ProMax. Okay? We're going to do it both in ProMax, actually the hard way and the easy way. But we are going to show you the easy way to do it. We have tools to do this, but we are going to start by doing it the hard way. As I mentioned, there is a tool for doing this depressurization in ProMax, but we are going to go over the theory first and do it by hand. So the first thing, we're going to make our system as simple as possible because we are going to be doing it by hand, as I said the first time. And we're going to be looking at an adiabatic depressurization. We're looking at an adiabatic system. Adiabatic means there's no heat entering or leaving our system. This is important because that does mean there's an energy term we will be ignoring. If we had a fire case, of course, it would be non-adiabatic. There would be a Q or an energy term we would have. When we're modeling an adiabatic system, there's a few points that are important to mention. When we set our system, we're going to be setting it as a fixed amount of, or we're going to be removing a fixed amount of mass in discrete increments. What I mean by this is if I have a vessel and it's got 1,000 pounds in it, 1,000 pounds of material, I am going to be taking out 10 pounds of material at a time. I'll take out 10 pounds of material, reflash, recalculate, and then do it again and again and again. I'm going to be taking out a fixed amount of mass in this calculation. Now, of course, as I remove mass from my system, the pressure of my system is going to drop. The pressure of a system with 1,000 pounds at a fixed volume and temperature is going to be greater than the pressure of the same vessel at the same temperature with half the mass. As I remove mass from this system, what is going to happen to the temperature of my system? Okay, this is an important question to ask. Now, of course, this is going to depend on the JT coefficient of my system, but for most hydrocarbon systems, when I remove mass from my system, as I drop the pressure, you get the JT effect and the temperature of your overall system starts to go down. Okay? This is particularly noticeable if you have a two-phase system. If you have a liquid and a vapor, as you start venting the vapor mass off, well, first off, let me actually take a step back and explain this differently. If I have a vessel and in it I have a liquid and a vapor in equilibrium, the vapor is at a higher energy state than the liquid. When I start to vent the vapor, I'm venting off the high energy state. This leaves the rest of the system at lower energy. Then, of course, I take some of the liquid and convert it into vapor, which of course requires energy to do that as well. So it gets that from the temperature of the system. So the overall temperature of my system starts to drop fairly rapidly in a case like that. With a single phase system, that's not quite as noticeable, but it is still there due to JT effect. Now, ProMax is a steady state simulator. When we are talking about removing mass over a period of time or depressurizing something over a period of time, we do need to account for time. How do we account for time? We're going to be doing things I mentioned in discrete increments. We're going to have a particular volume, a particular mass. We're going to start removing that mass. And every increment, we're going to consider new time step. Due to how we're going to do it, we are going to do it the easy way. We are not going to be doing it at a fixed time increment. We will be doing it at a fixed mass increment. This will make more sense as we move through. When we start to model this, there are a few things we do need to be aware of. First off, the total volume of my system will always be the total volume of my vessel, or the max volume of my vessel. It will remain constant throughout my depressurization. Now, of course, are there systems where the volume of the system changes? Of course, there are bladders out there that do adjust. We are going to ignore that case for what we're doing. We're going to ignore that case for the purpose of this webinar. There are ways to get around that, but we are assuming that the volume of our vessel is constant. This is important because the volume is constant. That is one state variable that is locked down. The volume will stay the same. The pressure will change, the temperature will change, but the volume will stay constant. When we are setting up our system, we need to set it up to where the initial pressure, temperature, and composition need to match the pre-relief conditions. This does not mean, and we'll go into this in more detail, this does not mean, for example, the values that ProMax is telling you in your stream or in your vessel necessarily, or in your separator necessarily, your pipeline. The conditions in that stream may not be the conditions in your separator, in particular if you have holdup times. We know the initial temperature, pressure, composition. We know the total volume of our system. Through each time step, we will subtract a certain amount of mass, and we will adjust our pressure to keep the same volume. However, we do need one more variable in order to calculate what our next temperature step will be. We need one more state variable. The state variable we will be using is our internal energy. We'll be discussing more why we'll be using our internal energy, but the short answer is, for our system, for a adiabatic depressurization case, we can say that the internal energy, the change in internal energy, is going to be equal to the enthalpy leaving my system. Let's explain why that is. Now, this equation isn't that complicated. Don't let it scare you. You're stronger than it, you're better than it. In this equation, this is the full energy balance for our system. We have the sum of our potential energy and kinetic energy as our system, plus the internal energy in our system, is going to be equal to the shaft work in minus the shaft work out, any shaft work we're getting out of it, plus any energy we're putting into our system minus any energy we're taking out, plus any enthalpy entering our system minus any enthalpy leaving our system. And I say enthalpy, technically speaking, it's our enthalpy, potential energy, or kinetic energy entering or leaving our system. So basically what we're saying is the total energy in our system is going to be governed by this expression. These are all the terms we could have. So this is the major equation that governs depressurization. In our system, let me actually talk about this briefly one more second. Most of this will go to zero. Most of these terms we can safely ignore. Let's talk about that. For example, in most cases, in most depressurization, you do not have shaft work. You don't have any sort of impeller in there. You're not trying to extract shaft work out through a turbo expander or equivalent. There's no shaft work. Because of that, our W term is zero, both W in and W out. If we've got a vessel, we can assume that there will be no or limited potential energy change. So our system isn't moving up very high, nor is it falling down very low. You can say, well, my depressurization is to the top. If I've got a liquid that's depressurized, it's got to move up to the top. That's fair. That potential energy change, considering it's going to be mostly in the vapor phase at that point, has a very low density. The potential energy change is going to be very small, relatively speaking. So we can safely ignore it and say it's zero or very close to it. As I mentioned, we're doing an adiabatic depressurization. So therefore, there's no Q. Therefore, there's no heat transfer. My Q is equal to zero. Because I'm doing a depressurization, I'm not putting mass into my system. So therefore, all my in terms, meaning Q in, work in, enthalpy, potential energy, kinetic energy in, those are all zero. None of those are entering into my system. Furthermore, I can say there's no kinetic energy buildup in my system. If I have a vessel, I'm not having kinetic energy slowly increase over time. Because of that, I can say my system kinetic energy is zero. There is only one stream leaving. Therefore, I can throw out the other in stream altogether, which all said and done, this leaves us with one simplified equation. My change in internal energy, I'm pointing to my screen, you can't see it, let me use the mouse. The change in my internal energy is going to be equal to my enthalpy plus kinetic energy. Now, for those of you who are a little more observant or were paying attention, you'll notice that I'd said initially my internal energy is equal to my enthalpy. Well, what about this kinetic energy term? I have a system that is, for all practical purposes, stagnant. I'm not going to look at the molecular level. Of course, the molecules are moving very fast. It has to do with temperature and entropy. We're going to ignore that. We're saying the system itself isn't moving. But once I open a valve, all of a sudden I go from zero kinetic energy to some kinetic energy. Isn't that important? Do we need to worry about it? So let's look at that. Let's examine this kinetic energy term. To determine how much kinetic energy and whether it's worth including, the important thing isn't necessarily whether kinetic energy has any sort of value, because it does. It's whether that kinetic energy term is comparable to my enthalpy term. If my kinetic energy term is small compared to my enthalpy, I can ignore it and say it's irrelevant. So let's look at it and compare it to our enthalpy. To calculate our kinetic energy, we have to remember kinetic energy is equal to 1/2 mv squared. Well, for a generic system, I don't know what m is. I do not know what mass it is. I don't know how much mass I'm removing. But I can say, if I'm comparing it to my enthalpy, I can factor mass out of both of those terms, because the total enthalpy I have is going to be a function of the total mass I have. So if I factor m out of that equation, I would have how does my specific kinetic energy compared to my specific enthalpy. So 1/2 v squared compares how to specific enthalpy. And so then when we look at our specific kinetic energy, it's 1/2 v squared, which is going to be strictly a function of the velocity of the exiting fluid. So what is the velocity of my exiting stream? So looking at that, let's look at the worst case. Because if in the worst case my enthalpy is small, I can say, well, then I can ignore it in non-worst cases. The worst case would be a sonic flow, where you have sonic fluid leaving through your valve, okay? Leaving through your system, extreme choked flow. Now, of course, we could get into a very long discussion about what is the speed of sound and why does it change. We could look at speed of sound as a function of pressure, temperature, composition, all this stuff. I am not going to. For the purpose of this class, let's just simplify it And let's just say we're going to use atmospheric conditions. We're venting to, we'll assume our back pressure is atmospheric. We're venting to atmospheric pressure. We're going to pretend it's not really much of a function of composition. We'll say the speed of sound is the atmospheric speed of sound at standard conditions, so 343 meters per second. If we're assuming that velocity, 1/2 v squared, that gives a specific kinetic energy of approximately 25 BTUs per pound. Again, this number could shift a bit, but I wouldn't expect dramatic changes. So let's compare it then to our enthalpy. For a hydrocarbon system now, this could vary a lot based on your system. If you have methane, you have a specific enthalpy of about 2,000 BTUs per pound. For ethane, it's 1,200. And then for heavier hydrocarbons, it tends to be about 1,000. And again, in atmospheric conditions, it varies quite a bit. But you'll notice in all these cases, it is very small, or excuse me, very large relative to my kinetic energy. So, as I say in this final point here, our kinetic energy is generally speaking about 1 to 2% of our enthalpy value. So for the purpose of this exercise, we'll pretend it's 0. If we really wanted to include it, we could. So with that said, our enthalpy is significantly larger than our kinetic energy. We could include our kinetic energy term. It wouldn't be difficult to include that in our calculation. I'll show you when we do this in ProMax how you could do that. We're not going to in this exercise, simply for simplicity's sake, but you can, in most cases, safely ignore it. As I mentioned now, we know that our delta U, our change in internal energy, is going to be equal to more or less our change in enthalpy. So what we're going to do to put this into ProMax is once we know all of our initial values and set up our initial system, we are going to input these values into a scenario tool in ProMax. If you're not familiar with the scenario tool, please reach out to us after this course. We'd be happy to work with you on it. It is beyond the scope of this course to go into it. However, what we would do is you would set it up to where in this scenario, you would be reading into ProMax a mass flow, subtracting a certain amount, feeding in the new mass, and then subtracting a certain amount and feeding in the new mass. At each step along the way, we will be calculating a new temperature and pressure. Obviously, because this is, in reality, this would not be discrete, but this would be a continuous function. In ProMax, because it's a steady state simulator, we will be doing this in discrete increments. The smaller your increment, the less mass you removed at each step, the more accurate the result will be, but the longer it'll take to get there. How many steps you want to take is entirely up to you. Again, we do have a tool that will help simplify this and will calculate reasonable step sizes. For the purpose of this, for understanding the theory, we are going to be doing this. When we're setting up the outputs to our scenario, you do want to set up the outputs you're going to want to see. You will need to output the specific enthalpy for the purpose of calculation, but we are going to want to include, in most cases, things like the temperature, pressure, and anything else that you find would be interesting or useful to you. For example, if I wanted to include the kinetic energy term, I would need to include an outlet velocity. I think we've discussed all that. I do want to mention one more time, when we are doing this together, we will be doing this on a mass leaving basis. I'll be saying at each increment, we will be losing 10 pounds. This does not mean that it's going to be equal time. The time for 10 pounds to remove is going to change, of course. As the pressure of my vessel decreases, we will be venting less and less. We're ignoring the time factor for the purpose of this exercise, for the purpose of understanding concepts and simplicity. So now let's get to ProMax and do this. So as I've mentioned, we do need to set up the conditions for our system with the conditions that would be in our system right before depressurization, right before relief specifically. Okay. In this case, I've already created a stream for us, and I'm pretending these are the conditions right before relief. We'll be looking, once we get to the fire case, how to create these sort of conditions. For simplicity and time's sake, we are just going to start it right before relief conditions. We're going to pretend that my relief temperature is 100 degrees, my relief pressure is 1,000 pounds, and that the mass in my vessel at those conditions is 1,000 pounds. These are all assumptions I've made. Furthermore, I've assumed that my total vessel volume is 302 cubic feet. You'll notice these are all per hour. That's because ProMax is assuming flows. Ignore that. The important thing is that your time, the time unit here is the same. If I had this pounds per minute and this cubic feet per minute, fine. That really doesn't matter. The important thing is that I keep the same time unit. A couple of points worth mentioning. This vapor volumetric flow, if we change our liquid volumetric flow to the same units, you'll see they're the same number. If you actually want to know the volume of vapor or the volume of liquid, you do have to look in these other categories. This volume here is the total volume. Not just the vapor, not just the liquid. In this case, of course, it's all just vapor, because I chose my system that way to simplify things. But it is total volume. The composition I selected was nothing fancy, primarily methane, a little bit of ethane, a little bit of propane. I threw in some butane, so good measure as well. If I was, the reason I did this strictly vapor was for simplicity's sake. If I have a strict vapor system, I do not have to worry about compositional changes. If we had a two-phase system, we would need to worry about compositional change, and how composition varies is a function of mass loss. I don't want to worry about that. And not only do I not want to worry about that, I want to make this as simple as possible because I'm doing it by hand. Again, ProMax has a tool we'll be showing you in a minute that will account for compositional change and all that good stuff. This exercise, and for us doing it by hand, we're going to make it simple. Now you'll notice, as I mentioned, we calculated this in terms of internal energy. Internal energy is equal to enthalpy. Well, technically enthalpy plus kinetic energy plus potential energy, but we're ignoring kinetic and potential. You'll notice nowhere in here are we, let me zoom in a bit so you can see it a bit easier. You'll notice nowhere in here are we reporting internal energy. So we do need to add that to our system. To do that, I'm going to click on the Options button, Stream Properties, and I'm going to go down to Internal Energy. I want total internal energy, so I'm going to add that. I could add mass internal energy. I could add molar internal energy. Not worried about that. I'm saying my total internal delta U is going to be my enthalpy change. So I do want to add my internal energy and press OK. You'll now notice that internal energy does appear in my system. I could move where I positioned it. I'm happy with it at the bottom. Once I've done that, I'm going to add a dummy heat exchanger. This heat exchanger serves absolutely no practical function. Well, that's not true. This heat exchanger is not going to be used. The energy stream on this is going to be 0. There's going to be no pressure change through it, no temperature change. I'm going to go to pressure change 0, temperature change 0. The reason I am doing this is because I'm going to put solvers on my stream here. And ProMax sometimes struggles to recognize, or it struggles to recognize itself when you are using solvers. So I'm making these two streams the same so that when I make changes in this first stream, I can read them from the second stream. This is strictly to make the solvers work right. Okay, this exchanger is a dummy exchanger. It serves no purpose. Or excuse me, it does nothing. So now, as I've mentioned, the volume of my system is 302. So what I'm going to do is I'm going to put a solver on my pressure so that no matter what happens to my temperature or my internal energy or anything else, my total volume is always going to be equal to this number. So I'm going to copy this number, and then I'm going to put a solver on my pressure. Again, the purpose of this is not to show you how to create solvers. But if you do have questions about it, please feel free to reach out to us. We'd be happy to work with you on it. Again, I want to reference stream 2. It does struggle to reference itself, which is why we're doing what we're doing. Okay. So I want to set up a pressure, P2 divided by that number, minus 1. Wait. I wanted volume. I grabbed pressure. That's my mistake. I want the volume of my system. Excuse me. I even wrote down steps so I wouldn't make mistakes, and here we are. VV for vessel volume. I apologize for that. Vessel volume. Okay. So now when I solve this, it did solve. Okay. My total vessel volume is equal to this. Now what I'm going to do is I am going to create a user value. You're going to say, this is complicated, Jerry. Isn't there an easier way? Yes, again, there is. We do have a tool, so you don't have to go through all this. We are here to show you concepts. What I'm going to do now is I'm going to create a user value. This user value is going to be for the internal energy that I'm going to want in my system. I cannot set internal energy directly. So what I'm going to need to do is create a solver on my temperature to achieve the desired internal energy. So the ProMax knows what my desired internal energy is. I have to create a user value for it. Okay. The units I'm going to do are just going to be energy, okay, BTUs. I'm just going to call them U. That seems right. The initial value I'm going to want is I'm going to want this number here for my internal energy initially. Okay. I now want to put a solver on my temperature such that this internal energy is equal to the internal energy in my user value. Just to simplify my life, I'm going to copy this moniker clipboard. Now I'm going to create a solver on my temperature. I'm going to add the U calculated here. I'm also going to add the U that I want, which I'm going to get from the user value parameter. UD for U desired. I want these two numbers to be equal to each other. UC minus UD divided or minus 1. I am going to want to normalize these functions. You'll notice these are very large numbers. If I did absolute scale, we would be solving to a ridiculous degree of precision. No point in doing that. If I solve, make sure nothing changes, we should be good there. So now we've got a system. So if I change the mass, let me just show you here. What it will automatically do is calculate the new temperature and the new pressure to achieve whatever internal energy I set there. So if something happens and I go down to 990 mass, I solve this, you'll notice it runs around a bit, and it solves for a new pressure and a new temperature at those conditions. That's what we want it to do. Now, of course, we are going to want to adjust our U value. You'll notice these don't solve to exact numbers. I could tighten the tolerance in the interest of speed. I'm going to say 100.25 is the same as 100 and 1000.52 is the same as 1000. Okay, we are going to be adjusting our UD again, this value here, the desired internal energy. And we are going to be adjusting the mass in our system. To do that, as I talked about before, we'll need to create a scenario tool. I'm going to do that by clicking Add Excel Workbook. With that said, we're going to set up some columns we need. The first column I'm going to set up is runs. You do not need this column, but I do, this is just a holdover from grad school. I do like to keep track of what I'm doing at each calculational step. I'm going to put in a category for mass. This is going to be the mass in my system, okay, at each individual step. I'm going to want it in pounds. The exact units don't matter. We just do need to be consistent. Now, ProMax does report pounds per hour. Again, I'm ignoring time. I'm going to put in temperature and pressure. ProMax does, or we are not going to need these values to do the calculations. I'm going to include them because if I was doing this, I would want to know these values at each point. If I wanted to, I could report the composition at each step. In this point, in this case, it's irrelevant because my composition isn't changing. I could report enthalpy shifts, specific enthalpy shifts. I could report all sorts of things. I'm not going to report any superfluous variables from this point forward. So now I am going to want to put out the internal energy. This is going to be a value that we read in from Excel. I want it to be in BTUs. Doesn't have to be, again, Mass removed. I could have a category for this. This is how much mass I want removed at each time step. I could just type in my mass directly if I prefer. I'm going to do it this way because this way allows us to see what's happening a little more clearly. Does not need to be this way. And then I'm going to need a column for enthalpy removed. This is again going to be in BTUs. I am also going to need my specific enthalpy. And this is going to be in BTUs per pound. So with this said, let's set this up. At each time step, I'm going to want to subtract. I'm going to use 10 because 10 is a nice round even number. Doesn't have to be 10. I chose this more or less arbitrarily. I'm going to want my enthalpy that's going to be removed to be equal to my specific enthalpy of my system times the mass removed. I'm going to want to feed in my system mass. My system mass is going to start off at 1,000 pounds. I'm going to want to feed in my internal energy. My initial internal energy is this number. So I'm just going to copy that and paste it here. Here on out, these are all going to be calculational steps. So I'm going to want my next mass that I'm going to be feeding into ProMax to be equal to that minus the mass I've removed. I'm going to need to carry this down first. Otherwise, it's just subtracting 0. There we go. This should work now. Okay. And that seems like a reasonable number of runs to me. My enthalpy removed is going to carry down here. My internal energy at each time step is going to be equal to my internal energy of the previous time step, or mass increment change, minus the amount of enthalpy I've removed from my system. These are all going to be the same at the moment, but as I have ProMax run through, what it's going to do is it's going to calculate my system with this mass and this internal energy, calculate my specific enthalpy. Once I have a specific enthalpy here, it'll adjust this value for the next calculational step. So now I'm going to add a scenario tool. Again, kind of beyond the scope of this course to explain where this comes from, but we'll put it in here. I'm going to call this mass. This is going to be the mass I'm feeding into my system. I want to put it into stream 1, phases, total, properties, mass flow, and I want to grab it from here. So ProMax will grab this mass, then that mass, then that mass, and so on and so forth. I check units, pounds, I'm happy. I'm going to add another variable, internal energy. Again, ProMax cannot read internal energy directly. You can output it, but I've set it up in such a way that I can feed it into my user value set for my desired internal energy. And I'm going to output it, or I'm going to grab it from here. And this is in BTUs, that's in BTUs. That's all the variables I'm going to feed into ProMax. I'm going to give it a mass and then an internal energy at each step. The other calculations I'm going to do in ProMax and in Excel. Then I'm going to output some variables. I'm going to output the temperature, because if I'm doing depressurization, I would like to see what's happening to it. Temperature, degrees Fahrenheit is fine with me. Pressure. I'm going to want the pressure here. Add variable, specific enthalpy. I'm going to go here, and I'm going to go down to the mass enthalpy, BTUs per pound. Fabulous. And then we're good. I am going to, for the moment, just do one run to make sure everything is in line and is working properly. I know what a temperature I expect. I know what pressure I expect. If I got very different values for this, I would need to double check and make sure that I've typed everything in properly. Now that it looks like everything's typed in properly, let's run it and see what's happening. Now we can see that my internal energy is changing at each time step. My pressure is changing and my temperature is changing. My temperature is changing to match this internal energy with my stream's internal energy. This internal energy is changing to be the value of my previous internal energy minus the enthalpy lost from the system. And of course, my pressure is changing to match the total vessel volume, which is fixed. We could allow this to float. I could have made my vessel volume change as a function of mass lost. This would be something I could do. Okay, if I had, for example, a bladder. I could have set it to where I did have a heat stream entering this. All of a sudden, my heat exchanger wouldn't be a dummy heat exchanger anymore. It would, in fact, serve a purpose. It would have a fixed energy into it. We could do a lot of things with it. We kept it simple, but know that there is nothing we have done that we couldn't add to. No terms that we ignored that we couldn't put back in the system. We talked about velocity. I could, or for kinetic energy, I could have put a pipeline here, and we could have just taken this flow, known what pipe it was feeding, the diameter of the pipe it was feeding into, calculated the velocity of our exit stream, which would have allowed us to calculate our kinetic energy at each term, at each time or mass step, which were mass increment, which would have allowed us to take our enthalpy removed plus our kinetic energy and subtracted both of them, or the sum of them, from our internal energy. We made a lot of simplifying assumptions initially. We said, all right, we don't have energy coming in, we don't have mass coming in, we don't have kinetic energy, we're ignoring kinetic energy change, potential energy change, but there is nothing in that major equation, in that governing equation, that we had to throw out. We threw it out to simplify things. But if you have a depressurization case where these things are not ignored, it would be very easy to plug them in and do this exact step. Now, of course, the question we all run into is, all right, this was done for fixed mass removal agents. What if we don't care about how much mass was removed? We want to know how long it took to remove it. Then we'd have to start bringing in other things. We'd have to bring in a valve. We'd have to bring in our pipeline and figure out which one was our limiting case, figure out how long it took to remove 10 pounds at this pressure and temperature. And then we could figure out a time there. And then we could figure out how long it took to remove 10 pounds here at these conditions, and then put the time there. And then we would have a variable time step. We would have a fixed mass time or a fixed mass step, but a variable time step. These are things we could add to it. We have simplified a lot of things. We've made a number of assumptions. The assumptions were very good, solid assumptions, I feel. So now that we've looked at adiabatic depressurization, let's look at depressurization with an energy stream, a fire case, if you will. Now, this is harder, but we're going to make it easier. And we're going to make it easier by using the tools ProMax has already inside of it to do this for us. What we did before was I showed you how ProMax does this depressurization, how you can do the depressurization. We've seen what's happening under the hood. Now we're going to show you a tool that we've got that already does this in a very similar fashion to what we did. So now let's look at depressurization with fire case. So first off, the Pseudo-Dynamic, we've already talked about this. The tool you're going to want to use is something called the depressurization example. It is found within the ProMax property stencils. This tool will do what we did with a lot more functionality. It will account for time step. It will allow energy. If we follow API 521, it can use that automatically to calculate our energy input. Lots of things it can do. It can also do a no energy input case, a full-on depressurization like we just did. It can also do fixed energy. If, for example, you've got a line heater or something equivalent, it can do that too. Now, something I kind of glossed over a lot last time, we're going to go into more depth, and that's how to create your relief scenario. When you have your standard case, your standard stream, you need to turn it into your vessel. You need to turn it into your pipe. You need to turn it into whatever it is you're depressurizing. And your stream doesn't really represent it. What I mean by is if I had a separator in ProMax, I had 5 cubic feet per hour vapor entering, I had 5 cubic feet per hour of liquid entering, I would have 5 cubic feet per hour of vapor leaving and 5 cubic feet per hour of liquid leaving. That is not necessarily what's inside my vessel. I do not have necessarily 5 cubic feet and 5 cubic feet. I could very well have something like 10 cubic feet and 50 cubic feet. I don't have anywhere in ProMax that represents this. I need to create something that does represent it. Okay? I need to create a stream that has the same ratio. Now, it does not matter, and we'll see this once we use the tool, if I get these numbers right, if I have 10 and 50 correct. That's irrelevant. What does matter is that I have the ratio correct, that I have a 1 part vapor per 5 part liquid on a volume basis. If I want to depressurize a vessel or a pipe or whatever, I need to know how much liquid is in there. Once I've got that done, we need to create it. When we're talking initial conditions, it depends on what we're doing. In ProMax, the depressurization tool has 5 options. Orifice diameter, time to reach target pressure, pressure after set time, pressure relief with time limit, pressure relief with temperature limit. These last 2 assume a conventional valve. These first 3 assume you have a rupture disc. This is depressurization with a rupture disc. This is depressurization with a valve. If you are doing the rupture disc, you are going to represent your conditions right before relief. If you're doing a valve, you can do it right before the fire. You can also do it right before the relief, but you can also do it right before the fire, so that way you can see your vessel increase. So you can see what happens to your pressure over time as the fire rages on. Okay, that choice is yours. But if you're doing a rupture disc, you want to do it right before relief. It assumes we know our operating pressure, it knows our operating temperature. If you know how much your vessel is full of, if you know your operating pressure and your operating temperature, you therefore know your operating density. That's because you know your composition, you know temperature, pressure. The fact that you know your density is very important, because we are going to assume that the density stays the same once the fire breaks out. We might be tempted to say our density changes. So let's talk about this. I think this is well worth discussing. Density is equal to mass times volume. If I have not let any mass, if I say our relief valve has not opened yet, the mass in my system before the fire and after the fire are the same. I'll say that again. If I'm not letting any mass into or out of my vessel, the mass in my vessel has to stay the same. I'm assuming the volume of my vessel stays the same. Because the volume stayed the same and the mass stayed the same, the density stayed the same. Because the density stayed the same, I can figure out the temperature of my vessel right before it relieves, because I know the relief pressure. So I know the pressure, I know the density, I can calculate the temperature. So if I were to create something in ProMax, let's run through an example. If I had a stream and it was operating typically at 250 pounds, 25 degrees, and my vessel had a maximum allowable working pressure of 500, and I had a system, might have a system that was modeled like this. No stream or object represents what's happening inside my vessel. I need to create a stream that does it. To do that, I will take this vapor flow and this liquid flow, and I will adjust their flow rates until I have the correct ratio of my vessel. So what I would do is, if I had a vessel that was 10 cubic feet vapor, 50 cubic feet liquid, I would change my vapor flow rate until this volume had a vapor volume of 10, and I would change my liquid flow rate until my liquid volume here was 50. Again, it's really the ratio that's important, but since we're doing it, may as well just do the actual vessel. Again, I need to create a vessel or a stream that represents my vessel. And I'm going to do that by adjusting the flow rate of my vapor, which I got from this vapor flow, and the flow rate of my liquid, which I got from adjusting this liquid flow. Once I have this, I have my vessel contents right before the fire. This is standard operating condition vessel contents. The composition, because I'm assuming multi-phase, is not going to be the same composition as this. It is going to be different. It may not even be similar, but it may be. That is irrelevant. The point is that I did recreate my vessel contents. Once I've done that, I can now simulate a fictitious fire. I can say, let's bring it to relief condition or right before relief conditions. To do that, I'm going to create a dummy heat exchanger. Unlike my previous dummy heat exchanger, this one serves a purpose. This one will be feeding energy into it. It will be feeding the fire into it. Because I know my maximum allowable working pressure, I know my overpressure, I know my maximum allowable overpressure, I know what my outlet pressure is. Okay, that will be the pressure right before my relief valve opens. Then, once I've done that, or I also know the density of my system. Again, just like I talked at before, the mass is going to be the same on both sides of the heat exchanger, and the volume is going to be the same on both sides of the heat exchanger. Because of that, because the mass is the same and the volume is the same, the density is the same. Because I know I've got the same density and I know what the new pressure is, I can calculate what the new temperature is. Because I know that, I can type in the density, I can put in the pressure, and I will get my relief condition. This relief condition is the stream that I want to run the depressurization tool on, because this is the stream I'm relieving. Not this one, not this one, not these. I'm relieving this. As I mentioned before, we give you two options. You've got the first three options in the depressurization tool that are for a rupture disc. We use the Crane technical paper to figure out the amount of mass that can flow through that. For the second case, it assumes, the fourth and fifth cases, it assumes a conventional valve. Because of that, the pressure as a function of time is going to look different in the two of them. In the rupture disc, you'll have your rupture disc that pops, and then your pressure will drop. For the conventional valve, it will come up, and then you'll see your pressure start to oscillate a little bit. It will not get all the way down, because if your pressure starts getting too low, your valve will shut. The rupture disc doesn't shut once it's open. This is why you do have different options. You can pressure relieve it over a time period, or you can relieve the pressure with the temperature limit. What sort of conditions you want to model before? Again, it is important, in particular with the rupture disc, that you set your conditions right before the relief. For the conventional valve, it doesn't matter quite as much. A few other things, and we will discuss these a little bit once we get into the tool. It does give you an option for the mass of the vessel. Okay, it says, how much does your vessel weigh, as well as what is the heat capacity of your vessel? The most conservative answer is to say your vessel weighs 0. This means that none of the energy is going into the vessel. Every lick of it is going into heating your fluid. If you have a vessel with mass and a heat capacity, some of your energy will go into heating that mass. It will ask you for your tank shape and surroundings. That's because you do have the option of selecting API 521 for heat estimates. If you select that, it will say, well, okay, that's fine. I need your shape and surroundings. It will follow API 521 for heat input to the T. You do not have to use 521 if you want, but if you do, it will require the same information that would require. There is a toggle at the bottom of that tool for using the equation of state for the liquid phase. What that means is whatever equations you are using to do your calculation in your system, it will use a standard equation of state to calculate your flashes. This is important if you're doing something like an amine system and you have an electrolytic model in your liquid phase. That can take a long time to do those calculations, and it doesn't add a whole lot to your system whether you use the electrolytic or whether you're doing just a standard equation of state. If you toggle that on, it will go much faster. You can use the electrolytic or whatever. If you keep that off, but it will take longer, be aware. And the record interval. This is the longest time step that ProMax will take. It can, and in fact, in many cases, will take shorter time steps, but it will not take a time step of longer than the record interval, or maybe record interval. I'm not entirely sure which one it's supposed to be. Both work. Regardless, it does not take a time step of longer than that. It will not output each of those time steps. If there is no appreciable change between two time steps as far as mass flow goes, it'll keep taking more. Or it'll go more longer before it records anything. However, it will do a calculation, take a calculation step of no longer than that value. With that said, let's open ProMax and let me show you how this works. So what I have here is I'm going to pretend that this is the contents of my vessel. I've already gone through the effort to make sure I've got the right ratio of vapor and liquid. These are the conditions of my vessel. These are not the conditions right before relief. These are the operating conditions of my vessel. I need to set this up to the right before relief conditions. To do that, what I'm going to do is I'm going to put on a dummy heat exchanger. I'm going to hook an energy stream up out of it and a physical stream. This stream on its outlet is going to have the same density. So I'm going to take this mass density and copy it. It is, however, going to have a different pressure. I'm going to say that my relief pressure, if I'm operating at 560, I'm going to say my relief pressure is going to be 688 pounds. So I'm going to go here and type in 688. You'll notice it now calculates a new temperature. It has a new fraction vapor. As I start adding energy to the system, I get more vapor. If I was displaying the actual volume flows, I would see the volume ratio change. I can add the volumes by clicking on Options, Stream Properties, and I could add volume fraction. Let's just add volume fraction vapor. And so I can now see my stream started off at 77% vapor. As I started adding energy, it went up to 79% vapor. Once I've recreated my conditions right before the fire, I now want to blow this down. I am going to assume I have a rupture disk. To do that, I'm going to go to More Shapes, ProMax Property Stencil. I've already added it, so it's here. I'm going to go down to the depressurization example. Take that, drag it out. This will take a minute. Ask me what I want to depressurize. I want to depressurize the stream right before relief. Now you'll notice something. I guess I should have mentioned this. You'll notice I did not put any mass flows in this. The important thing is the ratio. If I wanted to be precise, I could add mass flows to get the correct values. That's irrelevant. ProMax doesn't need them because it's going to ask me what my total vessel volume is anyway. It does read the composition and therefore the ratios. I'm going to put in my vessel volume. I'm going to say my vessel volume is 400 cubic feet. I'm going to give it an initial temperature and pressure. I have set it to the relief conditions. ProMax does not know that. I could be trying a conventional valve. And so I'm going to put those in. It was 139.1, I believe. Yeah, 0.01. I'm just going to put 139 then. Oh, as one note, as I said, rupture disk, these are the 5 options I talked about. These first 3 are rupture disk. These bottom 2 are conventional valves. So this is the initial pressure. Initial liquid volume fraction. I can go in to look at my stream, and I can see I'm 80% vapor. That means I'm 20% liquid. Again, right before relief. Initially, if we look at this stream, I was 23% vapor, 22.5. I'm 20% when I relieve. Does it change things very much? Probably not in this case. In some cases, it can be more sizable. In particular, if your relief pressure is notably different than your operating pressure. Okay. Target pressure. I told it I wanted to size an orifice diameter. Okay, what pressure do I want to relieve to? I want to relieve to half of my pressure, which is 644 psig. I say I want to get to half pressure in 15 minutes. That's what it defaults to. I could change it. Mass of vessel, I'm going to do the most conservative case and say there's no vessel mass. So therefore, it doesn't matter what the heat capacity of my vessel is. It asks, do I want to use API 521 for heat estimation? If I do not, all of these things are grayed out. I could also add in a heat input. If I'm doing depressurization, like an adiabatic depressurization like I did in the last case, I would put 0 in here. That would give me adiabatic depressurization. I don't want to do that. I want to use API 521 for heat estimation. I now enter this information as I know it. My tank shape, I have a horizontal cylinder. I'm going to say I have firefighting available. I'm sitting on bare surroundings. Put my tank elevation above grade. I'm going to say I'm, I don't know, 2 feet above. And my length to radius ratio, I'm going to say 8 because that seems like a good number. Unwetted area factor, API 521 assumes that your energy comes in more or less exclusively through the part of your vessel that has liquid. I do want to use the equation of state for the liquid phase. In this case, I don't know what property package we've selected. I don't know whether it would speed things up or not. And 10 seconds seems like a fine value for my maximum time step. Once I've done all that, I press solve. ProMax will now go down here and it'll tell us what's going on and what it's doing. You can see it's iterating through. At the first iteration, it guessed that we had a diameter of 0.05 meters. That was my error function. It said, no, that was too big. Let's make it smaller. And you can see it's slowly closing in on the solution. Depending on what we picked, it can go faster or slower. And there we go, and it solves. The most obvious thing it gives us is we asked it for an orifice diameter, so it gave us an orifice diameter. If I wanted to pressurize this stream down to 344 pounds in 15 minutes, this is the orifice diameter I would need. Now, of course, you wouldn't be able to buy, well, I mean, you could if you want to spend enough money, I suppose. You wouldn't buy an orifice with that size. There are standard sizes they would list. We go into it in more detail in our equipment rating and sizing class. For the purpose of this, we're not going to go into it. If you have questions, please let me know. But this is the orifice size that would get us to 344 pounds in 15 minutes. But ProMax gives us more than that. This is what I'm going to say the base amount of information it gives us. If you click on the results tab, it gives us a little bit more. Again, it tells us what values we've solved for, the orifice diameter. It also tells us, I'm going to ignore the max mass loss for one moment, the mass that's left in my vessel after 15 minutes, and how much mass was blown out during the course of 15 minutes. Furthermore, it tells us the average amount of heat that was put into our system. Now, both of these, mass loss, this is how much the maximum mass rate that was blown through our valve, or in this case, our rupture disc. The maximum mass that went through that disc. You'll notice this is a number that is larger than both my mass remaining and my mass vented. That's because I'm not depressurizing over the course of an hour. This would be over the course of seconds. The max mass that flew through my rupture disc was 3.2 pounds per second. That was my maximum rate. Average heat input, same thing. This is my average heat that went into my system. This is the average rate that energy went into my system. But ProMax gives us more than that. It also gives us these time curves. This is what is happening to my system as a function of time. I can take these, I can highlight them, and I can actually dump them into Excel, where I can look at this data and analyze it. So we're going to take this, I'm going to open up a blank Excel file here. Now I've pasted this into Excel. So now I could analyze this data and see what's happening. And I can say, all right, let's look at my pressure as a function of time. Okay. We can see it's not quite a linear function. We could look at, and this is going to be an interesting one, temperature as a function of time. You can see that it's actually increasing, even though I'm blowing down, even though I'm creating more vapor. That's because I'm adding energy to my system faster than it's losing enthalpy. The overall temperature of my system is getting hotter in this case. I do want to point this out. It will not get hotter in all cases. Oddly enough, even with a fire case, there are some unusual systems that I've run into where you can actually cool. Now, you're not going to cool very much, and you'll only get it in the case where your valve snaps shut. For this case, because this is a fire case, we are heating. If we look at, we can look at things like, for example, pressure versus mass loss. We can say, well, does my pressure strictly correspond to the mass loss? And you can see it's a far more linear function, although not quite perfectly linear. So you can ask all these questions, or get all these questions answered from these values and the time curves. But this is not all. ProMax also gives you the compositions. It says, all right, after we vented all this, this is the mass that's left in our vessel. This is the composition of what we vented. The sum composition, not the composition at each time step, of course. This composition will shift as a function of time. The composition of my vapor at first is different than the composition of my vapor later on. But it does report that. If my vent if I had some sort of max vent flow that was not at one of my ends, ProMax could report that as well. So with that said, that was what I had planned to cover for this course, or for this webinar. We've gone over adiabatic, what's happening under the hood with this depressurization. The depressurization tool is doing more or less what we did by hand. It's just doing it far faster, more efficiently, and more powerfully. It does have some limitations to it. If I had mass coming in, if my volume was changing, this does not allow that to happen. But I could still set that up and do that without too much effort, as you saw. Are there any questions? It looks like Wolfu has a question here. With 0, you assume the fire heat input is constant. We do end up assuming it is constant. Variable heat input along with liquid level drop. To the best of my knowledge, we do not calculate that. I would have to look into the code to see if that changes. I believe we keep it at whatever value your unwetted area factor is and keep it constant. That's a good question. But I can look into that, but I believe it is constant, yes. Hey, thank you guys. It's been great working with you, and have a good one.